Welcome to today's lecture, where we're going to talk about going beyond global sensitivity. Up to this point, we have focused on adding noise to a statistic which is calibrated around its global sensitivity. That is, we were really looking at the maximum over all possible neighboring datasets, all possible pairs of neighboring datasets. That is, we've looked at the quantity delta, which is the max over all possible x and x prime, which are neighboring, of the following quantity, f of x minus f of x prime. So this is looking over all possible data sets in the entire possible domain. However, this might seem a bit wasteful because, in fact, when we're adding noise, we're not adding noise to just any data set in the entire domain. We're adding noise to a very specific data set x. So naturally, the idea you might have is to look instead of the global sensitivity. So I'll just write this GS for the global sensitivity for now. Instead, you might think of looking at the local sensitivity of a function. So let's suppose we have some function f which maps from a domain x to the n to the real numbers. So for today, we're just going to focus on real valued functions. You can similarly define notions for multivariate functions. But the local sensitivity will be the following quantity. So delta sub ls for local sensitivity of a function f. We're usually going to drop that f when it's clear from context. And the difference is this time, this was defined in terms of the entire domain, but this will be defined in terms of a specific data set x, and it will be equal to the maximum over all neighboring data sets x prime of f of x minus f of x prime. So let me just write this explicitly. X prime is neighbors to x. So you can see here that it's maybe pretty intuitive what the difference between these two quantities is. This one looks at all possible neighboring data sets where x and x prime can be chosen from the entire domain. Whereas this one looks at a specific, you're just looking in the neighborhood of a specific data set x, which is sort of the one that's fed in. So this is the natural idea of what a local sensitivity is. The question is, does it work? So the natural type of algorithm you would think of is, okay, you before what we know is private, what we would do is you compute f of x plus, say, some Laplace noise with parameter delta gs over epsilon, and this was all good. This gives you epsilon 0 dp. However, let's try the local sensitivity type approach. The natural way you might think of doing this is, say, instead of doing the exact same thing as you did above, but now you just compute this quantity. And the idea is that, no, this will not be private. In fact, I'll sketch a very simple example for you where this is not private. And before I get to that, you should probably pause and think about why not. Think about the big difference between the local sensitivity and the global sensitivity, when the local sensitivity could be much less than the global sensitivity, and when this type of privatization according to the local sensitivity of the function is not really something that'll privatize it, and why not? I think these are fairly intuitive things, once you find the right example. So it can be pretty instructive, I think, to think about yourself and really figure it out. So I'll pause here for a sec, and you should pause the video and see if you can figure it out. So, okay, let's see. The benefits of this will be clear in the sense that sometimes the local sensitivity of a function around a specific database. Oh, sorry, let me be a bit more clear here, actually. This is not perfectly clear here because, like we said, the local sensitivity is defined in terms of a dataset x. So yeah, that's what I want to say, but nonetheless, even with it properly written as here, that is still not going to be private. And let's see what goes wrong. So the first thing I want to observe is that the local sensitivity of a function can be much smaller than the global sensitivity of a function. They can be very different quantities. But let's look at a simple example. So the example we're going to look at right now is the function f where f is, let's say f of x rather. So this computes the distance between, like it outputs the distance between the two closest points in the dataset x. So we'll just write this, dist between two closest points in x. So we will note that this could plausibly be an infinitely sensitive function, where like the domain, let's say, where x is in r to the n. So we'll say that we'll observe that this could be an infinitely sensitive function. For example, if you just have, say, 2 points in your data set, then they could both be equal to 0. And then, you move 1 point off to an arbitrarily large number, infinity, then the distance will go to infinity. So like, let's just sort of summarize that. Delta GS equals infinity. Yeah, I'm not going to write out the example, but as to why it can be, but let's just consider x equals 0. I'll write it, I guess. X equals 0, 0. X prime equals, say, 0, infinity. So that is a case where, this signal shows that the global sensitivity can be infinite. But however, let's consider, we can see that in some cases, the local sensitivity can be much smaller. So the local let's consider the following data set. X equals the following. X equals, say, 0, 0, 0. Now, what is the local sensitivity here? It should be pretty easy to see that any type of neighboring data set will have also f of x be equal to 0. For example, consider, so like my claim right now is that delta ls of x equals 0. And this isn't too hard to see. Consider, say, x prime equals 0, 0, infinity, the same type of thing we did before. Well, in this case, you can see that the nearest distance between 2 points is equal to 0 nonetheless. And you can change the third point to whatever you want, but really, this should be what you arrive at, that the local sensitivity is equal to 0. So what does this mean? If we try this type of algorithm, then it says that f of x plus the Laplace of, say, 0 noise is just equal to f of x. So what I'm trying to say here is, if we try to use this algorithm to privatize this function on this data set, where we just add noise proportional to the local sensitivity, so this would just output 0 deterministically. There's no noise being added. All right, so that's a constant. That's quite convenient in terms of the accuracy. It's very accurate. It's just going to tell you exactly what the value of the function is. But the question is, will it be private? And the answer is no. And we'll see an example as this sort of like a vague example. I'm not going to formally prove it to you that's not private, but it should be pretty easy to see. We're going to illustrate why this is. Consider the input x prime equals 0, 0, say 10,000. Now, the question is, what is the local sensitivity of this? Well, you can see that the delta ls of x prime is going to be equal to 10,000. Where did I get this number from? Well, you can say, changing, you can change the third element here, and that'll leave the value of the function at 0. But for example, if you take one of the zeros and change it to less than minus 10,000 or greater than 10,000, then you'll see that the closest distance between, or say, I guess, greater than 20,000, you'll see that you can move this one of these zeros arbitrarily far, and the most this value can be is 10,000. So therefore, you can see that the local sensitivity is bounded above by, say, 10,000. So now, suppose we want to privatize this on, we want to privatize a statistic on, say, the data set x prime. Then what we would do is add Laplace of, say, 10,000 over epsilon noise. So, and this is equal to, like, that's exactly what it is. So then this is going to be a distribution which is, I guess this is going to be equal to, let's say, Laplace of 10,000 over epsilon. So now I want to draw your attention to something here. So the algorithm, if it was given in X, then it would output 0 deterministically. And if it was given the input X prime, which is indeed neighboring, it'll output a sample from the Laplace distribution with parameter 10,000 over epsilon. So in other words, these are two neighboring databases, but the function when evaluated on these two neighboring databases is going to be very different. In particular, you'll be able to distinguish, a sample from just the number 0 and the number 10,000 over, and a sample from Laplace 10,000 over epsilon very easily. Yeah, so like an adversary could identify whether it's X or X prime, and you can see that very clearly. If you do the calculations yourself, you can verify this, but even just intuitively, it should be clear that this is not going to be private in any meaningful sense of the word. And so you can see the issue that really came up here. The issue is not with, the issue is with the amount of noise we really added. And that kind of was a sensitive quantity which we released. So, if we could say privately find out the local what we did, we kind of cheated by just looking at the local sensitivity and just added noise proportional to that. But it turns out that statistic on how large the local sensitivity is can be somewhat revealing. Yeah, like a data set can have low local sensitivity, but one that's right next to it might have quite high local sensitivity. So if we can sort of ameliorate these issues, then maybe we'll be okay. But yeah, we saw that this naive attempt at first just failed catastrophically, as we can distinguish between these two. But we're going to see that this local sensitivity type approach actually can have some merits. And if you handle things right, then you'll get some very powerful tools when it comes to exploiting the local sensitivity, which in many useful cases will get you beyond global sensitivity, as the title of this lecture suggests, and get you much better results, which are somewhat even instance dependent, we're going to say. By that I mean, potentially, it might be the case that solving the problem on a worst case data set might be impossible, but by using these types of approaches, you might be able to get something which is not quite as bad. So let's move on to the first approach. The first approach is a method which is known as proposed test release. This was introduced by Dwork and Lay in 2009. Yeah, so the issue with the previous example was that even though the local sensitivity on the dataset X was low, it was close to a dataset with quite a high local sensitivity. Therefore, based on how much the local sensitivity was, that really revealed something about the identity of the dataset. So we're going to try to see if we can get around that issue. And this time what we're going to do is we're going to try to privately check the distance to the nearest dataset with a high sensitivity. So in other words, let me say this a different way. We're going to try to verify that the dataset that we're looking at has a low sensitivity, but it's also surrounded by a lot of datasets with low sensitivity. If we can say that, then in fact the previous approach will essentially work. This is a rough idea. Well, I'll describe the algorithm more rigorously, but really that's what we're going to try to exploit. The idea that it's a low sensitivity dataset and it's around a lot of low sensitivity datasets. In particular, what we're going to do is check if it's a low sensitivity dataset and close to a lot of low sensitivity datasets, and if that's true, then it's going to be private to add a small amount of noise. But if it turns out that we detect that we're in a case like similar to before, where there might be a high sensitivity dataset nearby, then what we're going to do is the algorithm will just give up. It'll say, nope, I detected that I'm close to a high sensitivity dataset. Doing anything from here on out would kind of reveal that fact. So I'm just going to not try to even solve the problem anymore. And yeah, that's sort of going to be the approach. So like I said, the name of this is proposed test release, and this is kind of, what does this mean? Well, there's 3 steps which can be easily, decomposed into. So the first thing is it proposes, of course, it proposes a bound on the local sensitivity. So it tries to, as an algorithm or as an algorithm designer, we're going to say that I think the local sensitivity is at most some quantity. The next step is to test. Essentially test whether a bound is actually accurate. Is it actually, upper bounded by whatever quantity? And the third one is, of course, we release. So essentially, if we do indeed have a good bound on the local sensitivity, then you essentially do the previous algorithm that we said, fx plus Laplace of local sensitivity over epsilon. Yeah, and this turns out that it'll work. But this is like a vague description, but hopefully the 3 steps make sense. Propose a bound on the local sensitivity, test if it's accurate, and if it is, then we are going to release a statistic. Whoops, I've been using red this whole time, and I usually use black for this. Switch to that. So let's say what the algorithm is in a little bit more detail and a bit more precisely. So this will be the entire framework for the algorithm. Like, let me say that this describes an algorithm, but you should really think of it as a framework because there's some details which are not fully specified. And if you want to run this on any real setting, then you'll have to sort of specify it. So the first step is propose a bound beta on the local sensitivity at x. So essentially we guess a specific quantitative value beta. And then what we're going to do is, this is where it diverges a bit from the sort of vague description above. We're going to try to find the distance to the nearest data set where the local sensitivity is greater than this. So compute the distance between x and x prime, or let's just say x tilde, just to use a different symbol from before, where x tilde is the closest data set. Sorry, let me say this. The min over all data sets x tilde, where x tilde has local sensitivity, delta ls at tilde, is greater than or equal to beta. So what I'm trying to say here is that the first step we do is you find the nearest data set x tilde to the true data set where the local sensitivity on this new data set is greater than beta. Yeah, so note first of all that this could just be a distance 0. For example, if at the data set itself, if it has high local sensitivity, then it'll just be 0. But we're trying to say that, okay, what is the distance to the closest one, which has high sensitivity? Is it far away? We'd hope it's far away, but let's see. And so we're going to let gamma equal this quantity. We're going to let gamma equal the minimum distance to any data set which has high sensitivity. And here we're going to use what distance? Maybe this wasn't quite clear, but this is going to be the Hamming distance, which is the number of points you have to change to get from one data set to the other. Yeah, this is kind of, I think, intuitive in the sense of differential privacy, because like usually we look at neighboring data sets which correspond to Hamming distance of 1, but here we're going to find how far it is to the closest one. Okay, so that's an important quantity. The third step is we're going to privatize this. So we're going to compute gamma hat, which is equal to gamma plus Laplace of 1 over epsilon. I claim this is a privatization. I claim that this quantity here, this gamma hat, this is going to be epsilon dp. Why is it epsilon dp? The reason is because look at what we did. We computed this gamma here. This gamma is indeed a function of the data set. And what is the sensitivity of this data set? Or sorry, what is the sensitivity of the function gamma? Well, the sensitivity of the function gamma is going to be 1. And this is quite a convenient trick. Why is the sensitivity 1? Because we're looking at the number of points we have to change to get from one to the other. So therefore, if we look at a neighboring data set, x prime instead of x, then in fact, this distance it might stay the same, it might increase by 1, it might decrease by 1. But since we're looking at the number of points changed, you can see that very easily that the sensitivity of this function is going to be equal to 1. And this is a very useful trick that comes up a lot, let's say in differential privacy, where you can privatize it, where you can make it a sensitivity 1 statistic just by looking at the number of points to change to get from one to the other. That's, that'll be it's very useful to get a sensitivity 1 statistic, which is kind of the holy grail in differential privacy, low sensitivity statistics. That's a sensitivity 1 statistics, and therefore we can just privatize it using the Laplace mechanism. At this point, the algorithm is not too hard. All we do is see if gamma hat is large or small. So step 4 is if gamma hat is less than or equal to, say, ln of 1 over delta over epsilon, return just what we call bot. And I guess so one thing to make clear is before, when we vaguely described this algorithm, we just said what we do if it is a low sensitivity statistic and everything around it is low sensitivity. But we didn't say what to do if it's close to a high sensitivity statistic, and what we're going to do is just return bot. We're just going to say, okay, we can't do this, let's give up. And why does this correspond to this case? Well, recall that gamma was the minimum distance to a high sensitivity data set. So what we're saying is that it's if gamma is small, that means that it's either sensitive or it's close to a high sensitivity statistic. So if gamma hat, the privatization of it is small, then we're going to say it is a high sensitivity data set or close to 1, and we can just return bot. On the other hand, what if gamma hat is large? So if gamma hat is, say, greater than ln of 1 over delta over epsilon, then we're going to do as we said before, we're going to return f of x plus Laplace of, say, beta over epsilon. That is, what do we return? In particular, you'll see that essentially what this did was it checked if this bound on the local sensitivity was good, and if it's so, and we're far from any data set which this bound doesn't hold for, then we can just return the statistic with noise added proportional to this. So that's the whole algorithm. It's very sort of simple as we stated here. Let's see, how do we compute this? Is it easy to compute? Well, how long is each step? The first step, how long does it take to compute each step, rather? The first step in which we propose a bound, of course, that's a very easy thing to do. And similarly, 3, 4, and 5, you can see these are all very easy to do. But the main expensive part is this part right here. In fact, this might not be computationally efficient. It might be hard to do in general. Because why is that? Well, one thing we have to do is we have to, say, compute the local sensitivity of a specific data set. Sorry, the local sensitivity at a specific data set. That, first of all, might be expensive to do. The reason being that, maybe it takes at worst sort of n times the size of the domain. So let me just write this out. So computing ls, the local sensitivity, might be, in the worst case, say n times the size of the domain, which could be expensive somewhat. But the more troubling thing is this is a minimum over all possible data sets in the whole set. So in the sense that, to compute this min, it might take essentially size of the domain to the n. because that's the number of possible data sets you might have to consider. So this is not computationally efficient. In fact, it's rather slow. Now, that said, there's certain cases where you can compute this sort of distance to the distance to a highly sensitive data set. For example, the median is perhaps the canonical example where this can be done computationally efficiently. So I would recommend you try to just work it out. See how you would compute the minimum distance to a sensitive data set for the median. Okay, so the next part of this lecture will prove that this algorithm is 2 epsilon comma delta differentially private. And let's see how we would do this. So intuitively, I'll give you a sort of intuitive description of how it works, and then we'll see the actual formal proof. So the first step of it will be really the following. We're going to be asking the following question: is the local sensitivity low? And that's kind of up to roughly, say, line 3 and the if statements in line 4 and 5. So roughly above here is step 1, where we check if the local sensitivity is low. Remember, before, what we did when we were trying to do the sort of straw man argument at the beginning, what we did was we just looked at gamma itself, but gamma might reveal information about the data set itself. So instead, what we have to do is we have to privatize it by adding Laplace noise. So this step overall takes roughly epsilon of the privacy budget. And if we get past this part and we see indeed that it is a low sensitivity statistic and far from anything that's low sensitivity, then we, output this, which costs us another epsilon in terms of our privacy budget. However, there's a chance that, this log 1 over delta gives a bit of slack. In particular, there's a probability delta that we might have been wrong in terms of estimating whether the sensitivity, the distance to a sensitive data set is large or small. So the sort of epsilon delta part comes in by, the probability that it could be wrong between steps 4 and 5. So that's like a vague idea, we pay epsilon for the first half, we pay epsilon for the second half, and we allow an additional delta in the delta approximation in case we were wrong here. Okay, so let's actually prove this formally. So what is the theorem? The theorem is the following: that PTR, proposed test release, is 2 epsilon delta dp. Great. So let's see the proof. The proof starts, first of all, by considering the probability. And for shorthand, we're going to call this overall algorithm the same thing we always call these algorithms, m of x, for shorthand. So it's clear what we're going to refer this as. So the proof is the following. First of all, we're going to look at the probability of outputting bot under neighboring databases. This is done deterministically whether or not this gamma hat passes some threshold. So the idea is that since the probability that this gamma hat crosses the threshold is going to be done on, we're kind of seeing whether the probability of this, we're going to see the probability that gamma, after being privatized, whether it passes this threshold or not on neighboring databases. And since the sensitivity of the statistic is 1, and we add Laplace 1 over epsilon noise, it's not too hard to see that just by looking at the PDF of the Laplace distribution, that the probabilities will be related in the sort of the usual way. So let's write this out here. That probability of mx is equal to, bot. This is going to be in the following range: e to the minus epsilon, comma, e to the epsilon times the probability on mx prime is equal to bot. And again, this is just because of the fact that x and x prime are neighboring databases. The difference between gamma on one and gamma on the other is going to be at most a difference of 1. and therefore the the fact that we're adding Laplace noise to it implies that we're going to have this following relationship between the two probabilities. Pretty similar to before. So now that we have this sort of fact, which will be useful, what we're going to do is we're going to separately consider databases X that have low sensitivity and those that have high sensitivity. So sort of case one will be the following, when the local sensitivity is large. So suppose we're looking at a specific data set where the local sensitivity is large. So then in this case, since the local sensitivity is large, then in this line here, where we had where we computed gamma would be equal to 0, because in fact you have to change 0 points to get to a high sensitivity data set. So in this case, we have that gamma is equal to 0. And from this, we have that the probability that gamma hat is greater than this threshold we had, ln of 1 over delta over epsilon. This is going to be less than or equal to delta. So in fact, I think it's going to be exactly delta. But so we have this probability here. So in other words, this is equivalent to saying that the probability of m on x being not equal to bot is going to be less than or equal to delta. Okay, so that's useful. Now, it's not too hard to prove the desired bound. So let's let T be some subset of the output domain. So remember, we're looking at real valued functions, but we're also combining this with the symbol bot in case the algorithm just decides that it's going to, say, give up and not try to output anything. So let's look at some specific example here, some specific event rather. So what we're going to do is say that this probability, and we can break this down in the following way. I'll write it first and then we can explain it. So this is just saying that we're looking at the probability that mx is in some set t. So what we can do this is to break it down into the probability that mx is in t, and it's also in the symbol bot. Or we can say that it's either in that case or it's in the case where mx is in t and in the set of real numbers. So essentially, this kind of accounts for the case where it falls into step 4, and this one accounts for the case where it's the if statement is true in step 5, where we'll have we'll return a value. So here we can bound this as follows. We can bound this as less than or equal to the following: e to the epsilon times probability that m on x prime is in t intersect bot. We'll explain this in a sec, so don't worry. Plus probability that mx is not equal to bot. And this is also not completely obvious, but it's also an upper bound. So let's see both of these. So one thing to observe here is for any outcome which is a subset of the real numbers union bot, well, then this can either be one of two things. First of all, if they intersect, then it'll either just be the singleton item bot, or if they don't intersect, it can just be the empty set. That is, probability that mx is in some empty set. And that's a probability sort of 0 event or 1 event, or yeah, it's going to be the same either way in this case. So if it's this case, then it sort of vacuously holds, this inequality vacuously holds no matter what. Whereas for this, if it's just equal to just bot, then we actually have that from the sort of fact we proved before. So that's why this inequality holds. On the other hand, this inequality, why is this quantity less than the probability that mx is not equal to bot? Well, the reason is because t intersects a set of real numbers means that it takes some value which is not equal to bot, because that's sort of the remaining case. So this is always a valid inequality as well. And it's not too hard to complete the proof at this point, because here now all we have is just e to the epsilon. We can essentially remove this. We can remove this term here just because, removing some conditioning, it's not conditioning, I guess, removing the fact that this is going to just let it be in a larger set, and therefore the probability must be larger. So mx prime in t. So that's a valid upper bound for this term. And the other one is going to just be an upper bound on the probability that mx is not equal to delta. Well, we already upper bounded that before, but sorry, the probability that mx is not equal to bot, and we already upper bound this before as delta. So we have this here. And this is exactly what we wanted, in the sense that, well, it's even stronger than we were going for. We'll see where we pay in the other case, but you can see that this is exactly the definition of being epsilon delta dp. Good. Okay, so that's the case one, where we proved epsilon delta dp for the case when the local sensitivity is large. So let's do the second case where the local sensitivity is small. So case 2, where delta sub ls on x is less than or equal to beta. So in this case, we can actually view the algorithm as a composition of two differentially private algorithms, and just call it a day after that. So step 1, this is basically the way I broke it up before. The first algorithm is to release gamma hat. So remember, this is the privatization of gamma. So this is cos epsilon dp. And the second one is to, check this value. If gamma hat is small by chance, which it may be, then just release bot. But in the other case, we return something which has a valid upper bound on the local sensitivity, and it's something which is obtained privately. In particular, this part is release f of x plus Laplace of beta over epsilon. And if you just do the calculation, because of the fact that the local sensitivity of f at this point x is bounded by beta, you can see that this is actually epsilon differentially private. You might be wondering, why doesn't this contradict what we did before? Well, what we did before was we just plugged in the local sensitivity, which was obtained non-privately, and that caused the problem because that could reveal some information about what it is. But the post-processing guarantee of differential privacy is very convenient. That if you obtain something which is differentially private, then you can use it for whatever you want, and that'll still be differentially private. And composition as well lets us reason about it very easily. We have an epsilon here, an epsilon here. So overall, we have 2 epsilon comma 0 dp. Yeah, the key thing was that really we were only considering the set of all databases X where this local sensitivity bound holds. And indeed, thus we just released a privatization of that. And that concludes the proof. We looked at all cases. We saw in one case that it's epsilon delta dp, and in the other case, it's going to be 2 epsilon 0 dp, and therefore it's 2 epsilon comma delta dp overall, no matter which case it is. While the proposed test release framework is quite a bit more general, let's see a very simple application of it in the context of histograms. in particular, we're not going to look at the entire problem of histograms, but we're just going to look at a simple subcase. In particular, we're going to look at trying to compute the modal element privately. That is the most commonly occurring element. Yeah, you might think of this as an easier problem than computing the entire histogram. That is, what do we mean by computing the entire histogram? We mean that we want to get an estimate of every count of every item in the histogram, additive with only additive error in each one. But we'll see that we can essentially do it with the same type of accuracy for both settings. But the modal element is a lot easier to describe, and the algorithm we can actually tell you about today. Okay, so what I want to say is let's rewind before, where we back to the Laplace histogram. That was a case where we just added Laplace noise to every bin in the histogram. And in that case, you know, what type of error did we get? If you recall that we got the error on each bin, that is sort of the L infinity error, was approximately equal to log of the size of the domain. And this is not bad, you know, the domain size, paying only logarithmically in the domain size is pretty good. It's not polynomial, it's a very slow growing function. That said, it's still a finite amount, a quantity. Sorry, let me say it's a function that grows as the size of the domain increases. So in particular, if you had an infinite size domain, you'd be out of luck. There's nothing you can do with the pure DP histograms. Yeah, this approach is pure DP. So this approach is doomed if you have an infinite size domain. But the really miraculous thing, and this is kind of a surprising thing, is that if we relax to a prox DP, then in this case, we'll be able to get away with this. In particular, we'll have do away with this. We'll have no dependence on this size x, which is very nice. We can even have an infinite size domain and still get reasonable answers, assuming things are nice. And we'll see what I mean by assuming things are nice. So this relaxation will save you a lot. And like I said before, you might suspect that this is also due to the fact that we're going to be considering a simpler problem, but in fact that's not the case, and I'll tell you that a similar theorem holds afterwards for even the case where we want to estimate all of the quantities in up to some additive error. Okay, so this is the problem we're going to look at. So we have a data set problem. We have a data set x, which is in the domain x to the n. And we want to compute the most frequent element, which is, like I said, the most the mode. And so we can see that, let's just build some intuition first before we actually describe the algorithm. So let's suppose that the entire data set was just one value. It was just v. So, you know, x is equal to v, like where v is some value all the way up to, yeah, v. So the nice thing that we can see is that this is a very stable value. That is, what is the mode of this? The mode is v. If we change 1 point, the mode is still going to be v. In fact, all the way until we change roughly n over 2 points, we're going to have the mode being v. So this seems like a very nice setting where we can apply the proposed test release framework, just because of the fact that the local sensitivity is low. That is, the value of the function won't change at all as we change an element. And in particular, it won't change at all as we change many, many points, all the way up to half the data set. There won't be any change. So yeah, in particular, if we move fewer than n over 2 data points, we're going to have strictly more than n over 2 data points on this point v, resulting in the same mode. So this is kind of nice. And one observation I want to make is, in fact, the distance that we have to change it until the mode will shift is very easy to compute. So let me ask the question. How many points to change? Let's say how many points of x do we have to change before the mode changes? And by a similar type of argument, by just looking at what the modal element is and what it could possibly change to, well, this isn't too hard to see if you reason about it a bit. It's essentially looking at the number of, consider the mode of the data set. The first thing it could swap to besides the mode would be making the second most frequent element into the mode. And how many elements do you have to change from the most frequent to the second most frequent element to make that the new mode? Well, you can see that it's just equal to half their difference. So what do I want to say? Distance to a data set. Like, I guess I don't need to write all this. Let me just say that the answer to this, how many points need to change before the mode changes, it's approximately equal to 1/2 times count of most frequent element minus the count of the second most frequent element. And that's it. That's essentially, how many points have to be changed before the mode changes. Well, you'll note that this is also equal to the number of points, roughly maybe plus or minus 1, is equal to the number of points you have to change before the sensitivity increases. In particular, the local sensitivity is going to be 0 for when you have a very clearly defined mode, and where there's a gap of at least 1. But as you get to the point where changing a single point to when changing a single point would change the mode from one thing to another, then that's the point where you have a local sensitivity that's greater than 0. So in other words, this kind of tells you the distance to the first data set where the local sensitivity is non-zero, up to a plus or minus 1. So yeah, let's try to instantiate, like before we wrote this framework a little bit abstractly, but let me write it again for this very specific case where we can state it very succinctly. So it'll be the following type of framework. So step 1 is we're actually going to propose that the local sensitivity is less than or equal to 0. So we're going to say it's not a sensitive function at all. In fact, by this example, you can see that the local sensitivity on this data set is 0. And then as you go further and further away, even for many data sets which are quite far away, the local sensitivity will still be 0. So the next thing is we compute the distance to the nearest, we compute the distance to the nearest data set which has a local sensitivity which is non-zero. And like I said before, this is equal to roughly this quantity here. Gamma is equal to 1/2 the count of the most frequent element minus the count of the second most. There might be a plus or minus 1 here. I'm not going to worry too much about that because you're counting when the mode actually changes versus when you're next to the point where the mode changes. But don't worry too much about the plus or minus 1, at least for this lecture. So that's sort of the distance to the first database that has non-zero sensitivity. The next step is that we are going to privatize this. So compute gamma hat, which is equal to gamma plus Laplace 1 over epsilon. And step 4 and 5, let's just write them over here to save a bit of space. So if gamma hat is less than or equal to log 1 over delta over epsilon, then return bot. And the final case is actually quite interesting. What we're saying here, if gamma hat is large, that is, we're far from any point in which, we're far from any data set where the sensitivity is non-zero, then we can just output the value exactly. Like, remember before, we would just output fx plus our Laplace noise calibrated to this upper bound on the local sensitivity we had. Well, here, remember we proposed the bound of beta. So therefore, you can just output the function f of x exactly. You don't have any noise added at all. So then you just output the mode. It's a little bit surprising because you didn't have to add any noise at all. So it's surprising that you can output it exactly, but hey, if you do the analysis, it works out. So the claim is that, this algorithm here is epsilon delta dp. This is a bit better than before, which was 2 epsilon comma delta dp. And the reason is because here we didn't really have to do another instantiation of the Laplace mechanism if we're just going to output the mode without any noise. Now the question is, what type of accuracy does this guarantee? Well, you can see that if gamma hat is equal to or is greater than this quantity here, then we'll output the mode exactly. So another way of saying that is we get the answer right if we have gamma hat greater than this quantity here. Now we know that by Laplace tail bounds that sort of the probability that Laplace 1 over probability that a Laplace random variable with parameter 1 over epsilon is greater than ln of 1 over delta over epsilon is less than or equal to delta. So that implies that if the value of gamma hat is greater than 2 times this, then we're good. Then we're going to output the mode with probability 1 minus delta. So what we want, in other words, is that we want that gamma itself, rather not gamma hat, we want that gamma is going to be greater than or equal to 2 log of 1 over delta over epsilon. So that's what we want for gamma, and if that's so, then we'll output the mode with sort of probability 1 minus delta. And what exactly is gamma? Gamma is half the count of the most frequent element minus the count of the second most element. So in other words, we want that the most frequent element and the difference between that and the count of the second most frequent element, we want that to be greater than or equal to 4 log of 1 over delta over epsilon. So we need the difference between the number 1 and number 2 element in terms of their frequency to be greater than or equal to 4 ln of 1 over delta over epsilon. And if we have that, then we'll have the desired accuracy guarantee that the accuracy guarantee that we want is that we output the correct mode. So combining sort of this argument and this algorithm, then we get the following theorem. So this is basically what we just said. There exists an epsilon delta differentially private algorithm which identifies the most frequent element from an arbitrary data set with probability at least 1 minus delta, so long as the gap between the count of the most frequent and the second most frequent element is at least 4 ln 1 over delta over epsilon. And again, the sort of, let me emphasize a few points of this theorem. Like I said, these are stability-based arguments, and it's stability-based because the most frequent element is somehow stable because there's a big gap here. That's kind of like typical in this type of algorithm. And again, let me just point this out one more time because I think it's really amazing. But you don't have any dependence on the domain size at all. In fact, like you see an arbitrary data set. It could be like literally any type of numbers, real numbers, whatever. So that's very powerful. So this identifies the most frequent element. I'll claim, like I mentioned before, that you can do better. In fact, you can in fact do like a histogram which estimates the count of every element. And I won't like prove this here. I won't go into the algorithm even because it's a little bit more complicated. But I'll refer you to, say, theorem 3.5 in Vadan 17, his survey. And it gives a theorem of the following form. It says that there exists a differentially private algorithm which can, with high probability, output the count of every item in a data set up to an additive log 1 over delta over epsilon. So again, it can have an infinitely large domain, but still approximate up to this quantity. Compare with the epsilon delta dp, which would give you an accuracy of log of size of the domain divided by epsilon. So in a large or potentially infinite domain, this is much, much larger than what we have here. So that's kind of surprising and quite nice. Okay, so that's a proposed test release, which is the first method of getting bounds on the of going beyond global sensitivity and exploiting the local sensitivity. For the remainder of the lecture, I'm going to tell you just kind of briefly and quickly about two other approaches in how we might go beyond global sensitivity. And the first one is privately bounding the local sensitivity. So the idea behind proposed test release was saying that the local sensitivity was small for databases in a small neighborhood around the true database. So we're saying like kind of for everything close to the true database, it has a small sensitivity, upper bounded by some bound. So this allows the local sensitivity to grow. On the other hand, we're going to look at a different approach, which says, okay, you know, maybe it's too much to ask for to say that the local sensitivity is bounded everywhere in this like little neighborhood of databases. This time we're going to look at an approach which allows the local sensitivity to grow, but not too fast. We're essentially going to put a bound on the derivative of the sensitivity. So we're going to look at the sensitivity of the sensitivity. This might seem a little bit arcane, but I think it's a fairly intuitive idea once you think about it. Just considering the local sensitivity as another function of the data set, you can privately estimate that first, and then you can do whatever you want with it. In particular, you can just noise according to the local sensitivity instead of the global sensitivity. Yeah, I'm going to say that I don't have a good example of this, which doesn't involve you know, introducing a lot of new notation, but I'm just going to present it as is because I think it's fairly beautiful just by itself. If you want an example of this in use, check out section 3.4 of, again, Salil Vadan's survey, which has a nice one involving differential privacy on graphs, but that's a topic that I don't want to really cover right now, just because in the interest of time. So again, let me just sort of summarize how PTR kind of worked, proposed test release. It kind of guessed a local sensitivity bound. In comparison, what we're going to do, it guessed a bound and then tested if it was right. Now what we're going to do is estimate the local sensitivity. We're going to estimate the local sensitivity, and whatever we get out of that, which we hope will be accurate, then we use it when noising our statistic. So the analysis in the previous section will show that the algorithm that we come up with is epsilon delta differentially private. You can sort of work through it by just sort of looking at it before. So we're not going to repeat that analysis though. So let me just state one more time before I get to the algorithm. The idea in this case is that we're going to want to try to prove first a bound on the global sensitivity of the local sensitivity of the function on the data at the database X. So if we can do this, then we can just apply the Laplace mechanism as done. So let's see it step by step. So the first step, it's really only two steps to be honest. It's very, very simple. So we want to compute some gamma hat, which is equal to the following quantity. We're going to try to, again, privately estimate the local sensitivity of the function f. So f is our function at the dataset X. So let's skip ahead actually a bit. Like what I'm going to show you here is the sort of straw man algorithm I mentioned at the beginning. We're going to output f of x plus Laplace of gamma hat over epsilon. So what we have right here is the straw man algorithm that I mentioned at the very beginning of this lecture, where you just compute the local sensitivity on the database and you output you output the function applied to the database with noise calibrated to this local sensitivity. Now, like I said, this doesn't work, and we talked about some ideas as to why not. You know, the local sensitivity itself could be somehow revealing of which data set you're looking at. So what we're going to do is we're going to take this local sensitivity and we're going to consider this as a statistic itself and privatize it. So in particular, what we're going to do is we're going to add, you guessed it, Laplace noise. And how much Laplace noise should we add to this? Well, we're going to add Laplace noise calibrated to the sensitivity of this function. So literally all we're going to do is consider this to be a function and add noise calibrated to, say, the global sensitivity. I'll spell it out here explicitly. And where the function of that we're considering is exactly what we have here. So it's kind of weird because we're going to have some double superscripts here, but hopefully it'll make sense. Sorry, let me remove this, in fact. Yeah, okay. So this is the quantity we're going to consider, and then we're going to add a little bit of slack just to account for the fact that we want epsilon delta differential privacy. This is similar to how we added ln 1 over delta over epsilon in our bounds before, and we were thresholding with respect to that. So yeah, let's just take a careful look at this. What are we doing? Again, we take the local sensitivity, but instead of just taking that raw, like just without any noise or anything, we add noise proportional to the global sensitivity of this statistic. We add noise proportional to the global sensitivity of the local sensitivity. And if we can do that, then that gives us a private estimate of the local sensitivity, and then we can just plug it in and do the same analysis that we did before. So yeah, it's a little bit weird, but when you think of it as really intuitive, just considering the local sensitivity as another statistic you might want to compute and then privately estimate it. Privately compute it, rather. Now, while before I mentioned that proposed test release can be a rather high sensitivity, the proposed test release framework can be quite computationally expensive. This, on the other hand, is not generally computationally expensive. All you have to do is be able to compute. Sorry, I'll tell you what you need to do in order to actually apply this type of algorithm. All you have to do is, first of all, get a bound on the global sensitivity of the local sensitivity of the function. That's kind of what we do, not algorithmically, analytically. You have to, look at the function, try to find some bound on the local sensitivity. We've sort of done this for functions before when we were doing it in the straightforward way, but now you just have to do it for a very specific type of statistic, which is the local sensitivity of whatever function you want. So this can be done often without too much trouble if it's actually indeed bounded. And that's like something you have to do analytically. In terms of computationally, all you have to do is compute the local sensitivity at the dataset X, which is fairly comparatively cheap to do. We already talked about this before, but in the worst case, you have to consider changing essentially every data point. I guess that's n minus 1, really, not n. No, I guess it's n. So you take you consider changing every data point n, and you consider changing them sort of to every possible value in the domain. Here, I guess it's going to be size of x minus 1, because you have to change to something different. And this is the running time for computing the bound here, for computing this local sensitivity quantity. So in other words, compute this analytically, and then compute this sort of algorithmically. And then if you do that, then you're done. I'll mention that the local sensitivity can sometimes be done even faster than this. For example, in the case where we were looking at before when we were trying to find the mode of a histogram, that was a case where we could do it independent of the domain size just by looking at the biggest and the second biggest element. Sorry, which the most frequent and second most frequent element, rather. So similarly, you can do it faster than that sometimes, but yeah, this is sort of a worst case bound. And this is quite nice. This is the whole thing. It's a very simple, like, 2-line algorithm, which can often give you decently nice results. I think it's a nice approach, and maybe you should think about it sometimes. It's indeed far simpler but less powerful than the proposed test release. That took a long time to describe and analyze, but this just took like a very little bit to get through. All right, the final approach that I'm going to mention is a very powerful technique called smooth sensitivity. So this is going to be similar to the previous approach. Well, all of these are kind of related somehow. They all kind of try to exploit the local sensitivity of the algorithm, of the function on the data set. But this one is kind of similar to this one. What we did here was we said, okay, the local sensitivity, it may be able to grow as we go further and further away from X. We just have to say that it's actually not growing too fast. And so that's true of this and the next and the algorithm we're about to talk about. We want it to just essentially bound the rate of how fast the sensitivity can increase. So this method was introduced by Nassim Raskolnikova and Adam Smith in 2007. So this was like kind of in the early days of differential privacy, just after the first paper came out in 2006. So yeah, this is, unfortunately, I think this is a very powerful technique, but it's sorry, that's a fortunate part, but unfortunately, it can be a bit complicated. I'm going to try to just get across some of the intuitions, but actually to like analyze it in more complicated situations than the most basic ones can be a little bit of an ordeal. So I'm just going to describe it from a high level, and hopefully, if you're interested, which I hope you should be, check out the paper itself, and I think it's nice. Yeah, ask me for resources if you want to learn about it, because I can point you towards perhaps some of the best expositions for it. Okay, so right, let's think about once again back to the original example that we had here, where we were looking at the data set, which was just 0, 0, 0, and we were looking at the function, what is the minimum distance between any 2 points. We had the good thing that the sensitivity at the local sensitivity around x was 0. It was very small local sensitivity for data sets at distance 1. But when we went to data sets at distance 2, then the local sensitivity jumped up a lot. So that's something we'd like to really avoid. And intuitively, whatever local notion of sensitivity we do end up using should account for data sets for more sensitive data sets which are nearby, but at a discounted factor depending on how far they are from x. So we care a lot if a neighboring data set, if comparing with a neighboring data set, we have a high sensitivity. But if it's say like take 5 steps and now you get to something with a high sensitivity, then maybe we don't care quite as much anymore. So this is the intuition, and the correct way to formalize this is not at all obvious. So what we do is we define the smooth sensitivity of a function. So if we have a function f, then smooth sensitivity is the following quantity. And again, it's at a specific data set x. This is equal to the max over all data sets x prime. Let's say x tilde, because usually we use x prime for a neighboring data set. So we look at a max over all possible data sets of the following quantity. We want to look at what the local sensitivity is on f at this new data set x tilde times e to the minus epsilon times the distance between x and x tilde, where once again this distance is going to be the Hamming distance. That is the number of points that have to be changed to get from one to the other. So this is the smooth sensitivity of a function at a specific point x. So again, like I said, when d is equal to 0, let's say, then this whole term is equal to 1, and we want we want the local sensitivity to be bounded. But say if we have 10 here, a distance 10, then in fact we're going to be quite far out, and it's discounted. This will be a small term, and therefore this term here, the local sensitivity, can be correspondingly larger. Yeah. Again, I'll comment once again, just like proposed test release, this is not necessarily obvious how to compute this. In particular, it's taking a max over all data sets in the entire domain. So it's not obvious how to calculate, but nonetheless, in some simple cases, for example, the canonical case of trying to compute the median, it is still doable in polynomial time without too much trouble. There's actually, I think, near linear time algorithms to do that. So this is already an ordeal to calculate. But suppose we somehow magically get a handle on, the smooth sensitivity of a function. Well, at that point, there's one last surprise. You might think what you want to do is you might think that, okay, well, we computed some sort of smoothed out sensitivity. Well, what we're going to do is we're going to compute f of x plus Laplace of, delta ss of x over epsilon. Well, unfortunately, you'd be wrong. This is not the algorithm. What you actually have to do is you take f of x and then you add what's known as a Cauchy random variable. A Cauchy random variable with like scale parameter equal to delta of the smooth sensitivity over epsilon. Yeah. So this is not a Laplace random variable; it's a Cauchy random variable, which will give you epsilon dp. If you tried to do this, actually, I lied to you a bit. This would work, but it would give you epsilon delta dp for some delta greater than 0. But yeah, instead, if you want pure dp, you have to add a Cauchy random variable, which maybe you haven't even heard of before. But a Cauchy random variable is quite a sinister, a little bit of an evil distribution. Why is it evil? Just as one example of an evil property is that it doesn't have an expected value. There's no mean of this random variable, which is kind of like, the first thing you try to think about of any random variable. What is the expected value? It doesn't even have that. So yeah, that's kind of bad. And why doesn't it have an expected value? Well, the reason is because it has very, very heavy tails. So like if you look at, let me just draw you a very poor sketch right here. If you look at a Laplace random variable, it looks something like this. It's sort of exponentially decaying. That's a Laplace. If you look at, say, a Gaussian random variable, it looks something like, it actually decays even faster. It looks something like this. So you can see that once you get past a certain point, the tails decay very quickly, faster than a Laplace distribution. But a Cauchy distribution, on the other hand, I can't actually remember perfectly what it looks like. I think it looks something like this. But the point is it has much heavier tails. So they still go down, of course. They have to go down, but otherwise it wouldn't be a distribution. But they go down kind of very slowly. They only decay polynomially, whereas the other ones decay exponentially. So yeah, let me just label these. And then this is Gaussian. So the idea is it's a little bit of an evil distribution, and it has very heavy tails. As a result, when you add this Cauchy noise, you might not have the same sort of strong concentration properties that you might have if you're looking at Laplace and Gaussian distributions. In particular, remember all these times we got log 1 over deltas and everything, or log of the domain size. Those type of things won't really happen for Cauchy random variables just because of the fact that they only decay polynomially. And if you try using a similar argument, yeah, you'll get the sort of polynomial decay instead. So yeah, again, there's only a very brief coverage of smooth sensitivity, but I think all three of these topics we've covered today, smooth sensitivity, privately bounding local sensitivity, as well as the proposed test release framework, all of these are very powerful frameworks which are very useful when, in particular, the global sensitivity might be too large or too difficult to deal with, or it might vary a lot and you really want to get beyond just the global sensitivity. So I think it's a good tool to think of in your toolbox when you're looking at differential privacy, and not just give up the first time if you see that the global sensitivity